Oh, does it? Yeah, that's probably when I'm walking back and forth. Yeah. Sorry, I try to stay here, but I don't like standing still too well, so.
Just remember to talk louder when you're walking.
Yeah. And the other thing is when I'm pointing, it's sometimes I like to point with the other hand, and I don't know. Anyway, let me go through a couple of these announcements. None of them are too crucial, I don't think. Yesterday was the 60% completion date for Title IV funds, whatever that means. I think it is if you got on federal assistance. If you withdraw them before that date, you pay them back after that date. You don't have to. That's at least part of it anyway. So anyway, that's all pretty much I see on the on the administrative calendar. Volleyball team will be playing, I think it's this evening, isn't it? Yeah, this evening, versus Gadsden State. That's a home match over on the Birmingham West Campus, Arthur Shore Fine Arts Building, which is also a gymnasium. The match will begin at 6 o'clock. Unfortunately, I'll be in class at 6 o'clock and probably won't get through until close to 7, so I doubt if I'll make much of the match there. But they are a very good team, so it's well worth talking about it, seeing them play. Now, this is something new. I'm sort of guessing you're probably not going to be too interested in it, but you may be. But some of the younger guys might be. But you might be. I don't know. This is from a woman named Christina N. Mora. She is a postdoctoral fellow in the microbiology department at UAB. And she said she is one of the newest cohort of merit scholars at UAB. I don't know what those are. She said she came across this 1-week summer opportunity for college students. So, if you qualify there, you're in college, so I guess interested in biopharma manufacturing careers. So I take that to mean biological, pharmaceutical manufacturing careers, and thought one of your students might be interested in applying. The students are paid. Now this, I find this pretty interesting. 1-week summer opportunity, it says, okay? The students are paid $1,000 and travel expenses are covered. And the application deadline is January. She doesn't say when in January, but there is a link here that you can go to and find out more. I thought, $1,000, they pay you for a week to see if you're interested in biopharma manufacturing careers. Oh, that's pretty incredible. $52,000.
Trying to create a field. You may not have many students know that it exists.
Right. Exactly. Mm-hmm. So that's the rate of $52,000 a year just to go see if you want to get hired.
You're talking big numbers. They said 1,000.
Yeah. Right. So now, what I did here, we have one more example to do in 13.5, but there wasn't a good, there wasn't a slide for it in 13.5, so I went on loaded 13.6 and then found a slide with a lot of white space in it. Hopefully we can work around that. So here's what we've got. Any questions before we get started today? I should have asked that first. All right. What we've got is an equation. Let me get my pen set up. All right. 3x squared z minus x squared y squared plus 2z cubed plus 3yz minus 5 equals 0. All right. Now, before we even get started on this, it's sort of a mystery to me why they write it like this. Of course, that is the form it needs to be. But why wouldn't they have written it is equal to 5 and then ask you to do whatever they said? And then you say, well, we have to get it in this form first. But they didn't have you do that. They wrote it in exactly the form you needed. Not that it would make a lot of difference. Okay? Now, what we're looking for is the partial of z with respect to x. The partial of z with respect to x. Now, it's a pretty interesting question because there's nothing in the way this is written that would lead you to guess that z was the dependent variable and x was one of the independent variables. Because frankly, I look at that, they all look pretty equal to me, okay? And you almost wonder, well, is there some other independent variable we're not seeing, like s or t or something like that? But no, this is what we're looking for. So the implication here is, if z were the dependent variable and x one of the independent variables, what would be that partial? Okay? Now, what's that?
The last question you said.
The last one?
You said if something were.
Yeah. I think what I said was, if z was a dependent variable, then x was one of the independent variables. Is that what I was saying?
I think that's what you
Okay, yeah. And this, by writing this down, that's implying that's the case. Okay, there's nothing looking at that would indicate one of these is that z would be dependent on x and y, say. And yet, the other questions don't have us do the same thing. All right. Now, their warning is to use the chain rule features up in Theorem 13.8. And frankly, I just wonder what would happen if we just started doing it. You know, taking I guess it's better to do what they say because it could take a lot of time to do it the other way. So let's just do it. How they approach this is say, let's let f of x, y, and z, and maybe that's why they wrote it this way, because this is how they're going to do the problem, is equal to this thing here. The 3x squared z minus x squared y squared plus 2z cubed plus 3yz minus 5. That's why they wrote it that way, equals 0, so you can set that as a function of the three variables. See, and by doing that, the implication is to me that f represents some other variable, like u or something else, and then you could do the various derivatives with that. But that's not what we're doing. We're taking the partial of z, which just looks like one of those regular variables, and it is of f with respect to x. And you remember what the rule was? Minus, that's good to do that. Okay, which partial? That's it, exactly. Okay? It seems a little bizarre, but it works, and you got to remember that minus sign's there. Okay? So, one of the first things we've got to do is take the partial with respect to x. And what would that be?
That would be 6xz.
Perfect.
Okay, and is it x squared y squared?
Second?
Is that x squared plus?
Yeah, that's minus x squared y squared.
Two x,
2xy squared. Got it? Yep. The rest is 0. Okay? Right. Yeah. So we have a minus 6xz minus 2xy squared. That's your numerator. Let's do the x sub z. See what we get as our denominator. What would that be? Three x squared. Perfect.
0.
Right.
Minus 6z
Okay.
squared.
Oh, it's a plus 6z squared, right? Did I write it wrong?
No, I wrote it wrong.
Yeah, I think it, yeah. Okay.
6z squared
Right. Plus 3y. Got it.
0, 0.
Yeah. All right. So that would be over 3x squared plus 6z squared plus 3y. Now, I can easily imagine spending a lot of time looking for common factors or doing a whole lot of things here and winding up with absolutely nothing to show for it. You could factor a 2 out of the numerator, 3 out of the denominator. That just gives you a 2/3 of something. But that seems like they do that. Oh, I see what they did. No? Make sure we did it right. Oh, I see. I'm looking at the wrong thing. Yeah. One only sort of correction thing they do here is take this minus sign, distribute it across the numerator, and that would then make a 2xy squared minus 6xz over 3x squared plus 6z squared plus 3y. Yeah. Okay. So 2xy squared minus 6xz over 3x squared plus 6z squared plus 3y. Yeah, done. The next part says find the partial of z with respect to y. Okay? We've already got part of that. Oh, what would that be then, by the way? Minus partial with respect to y over partial with respect to z, which we already have that denominator. So let's go on and write that down so we don't forget about it. 3x squared plus 6z squared plus 3y. Could factor out the 3 like I said, but yeah, not any real reason to. So the one other thing we need to do up here to figure out for down there is do the partial with respect to y. And what is that?
0 minus
Right?
x squared 2x squared y.
Minus 2x squared y. Perfect. Second, yeah, partial, okay. Yeah, we're just doing the partial of f with respect to y.
0 plus
3z, got it. Okay, so that would be a minus 2x squared y plus 3z. And then to get rid of the minus sign in front, negate everything in the numerator, you get 2x squared y minus 3z over 3x squared plus 6z squared. Oh, z squared. That's ugly. Okay. Plus 3y. Now, is there anything we can do with anything there? Really doesn't look like it, so let's see what they got. 2x squared y minus 3z over 3x squared plus 6z squared plus 3y. Just using the form they gave you, it's pretty straightforward. And nothing else you can do. Look for anything that you might be able to divide out. I see nothing. So that's finding the partial derivatives implicitly using that formula that we have. Now, what I was, well, let's not even mess with that. Okay.
Is that it?
That's it. That's all the answer is. You can't simplify it. That's it for partial z with respect to x. That's the one for partial z with respect to y.
What's this real? Why do we use this?
That's a good question. I think that realized systems can be very complex and have all sorts of weird, and whether one ever comes out looking like this, I'm not sure, but you can have all sorts of interrelationships. If you just take, for example, if you're trying to model the weather, you have to take into account temperatures and humidities and wind speed and pressure, atmospheric pressure and stuff. And you have to do this at various levels in the atmosphere. The jet stream could be going really fast up here one way, but things could be doing something different down below. And you have all those, so you wind up with just tons of variables there, and you want to find out how one of them is relating to the other. Or if you can manage to write down some sort of an approximation of how these all tie together, and then get all those on one side of an equation equals 0, name that your F, your G, whatever you want to call it, and then take the partials just of the ones that you're interested in. The one that you're wondering how temperature at the mid altitudes is affecting the wind speed on the ground, or something like that. This would be at, dz, partial z with respect to y. Now that's assuming you can come up with an F that describes all those things for you. That's probably a pretty lousy example, but I do know that there's lots of things in nature that have multiple dependencies. And if you can come up with some sort of approximation of how they do sort of interact and interchange with each other, then this is a pretty handy tool for seeing how it might benefit, how one change may affect the other. Because what are you doing there? You're assuming everything else is constant. This is assuming that the y's are constant. This is assuming the x's are constant. So just how is z, whatever that is, while that was of interest to you, is being affected by just one of the other two and not both. That's my, right off the top, by all I can do. The Homework exercises I think I've assigned before, either 3 or 5. They're both at Calc Chat. 3's at Calc View. Any of the odds 7 through 11, they're all at Calc Chat. 9's at Calc View. 13's at Calc Chat. 15 or 17 are at Calc Chat. 15's at Calc View. 19 or 21 are at Calc Chat. 19's at Calc View. 23 or 25 is at Calc Chat. 23's at Calc View. Any of the odds 27 to 33 are at Calc Chat. 31's at Calc View. 35 and 37 are all at both at Calc Chat. They should be anyway. 39 and 41 are at Calc Chat. 43, using a table of values, that should be at Calc Chat. 45 and 47, you can explore using those. If you want, they should be at Calc Chat. And then any of the odds, 49 to 55, should be at Calc Chat. Okay. Sorry, I've got such a frog in my throat. I think I ate too fast and didn't drink enough fluid while I was eating, so hard to breathe. So anyway, you need this one any longer? Okay. Let's go on and erase that and back up. All right, chapter 13 is still functions of several variables. 13.6 is directional derivatives and gradients. Okay? And just looking at this, I think this is going to be this section's picture here, because you definitely have a gradient there. You're going uphill fast from there. He's on a fairly flat spot, but it's not going to last for long. Okay, that's what we're talking about with a gradient, a change. So, objectives here, find and use directional derivatives, which also probably is going to be defining what directional derivatives are of a function of two variables. Find the gradient of a function of two variables. Use the gradient of a function of two variables in applications, and then find directional derivatives and gradients of functions of three variables. Okay, so start with it's really 3 dimensions, because two independent variables, one dependent variable. So that's 3 dimensions. This is 3 independent variables, and a fourth that's a function of those. So, directional derivatives, what in the world are those? You're standing on a hillside represented by Z being the altitude of the hill, is a function of x and y, where x is, say, the north-south direction, and y is the, let's say, east-west direction, y is the north-south direction, okay? Or something like that. Here's the figure they're referring to, okay? And you want to determine the hill's incline toward the z-axis, all right? You already know how to determine slope in 2 different directions. Slope in the y direction, given by the partial derivative with respect to y of xy, and the slope in the x direction is given by the partial derivative of f in the x direction, partial derivative of f with respect to u. So what those are telling you, if you're someplace, say, pick a place, here, say, all right, the partial derivative in the x direction would be, looks like going downhill here. Slightly negative there. Partial derivative in the y direction also looks like it's going somewhat downhill. So it looks like those are both negative there, okay? In this section, you'll see that those 2 partial derivatives can be used to find the slope in any direction. Interesting, okay? So that's what we will be doing. To determine, to determine the slope at a point on a surface, you will define a new type of derivative called a directional derivative. So you're not just in the direction of increasing x or increasing y, but in some other derivative. Begin by letting z equal f of xy. That's going to be your shape of your surface, okay? That's your surface, okay? P of x0, y0 be a point on the domain of f, okay? This function on the domain of f is shown down here. And frankly, for the life of me, I do not see x0, y0 anywhere there. I assume this is the p they're talking about, so it's x0 would be, you know, fairly small positive, and y is even smaller positive, okay? Because it doesn't look like it's right on the x-axis, just off of it, okay? The direction of the directional derivative is given by the unit vector u. Here's your unit vector coming from the origin, standard position. And that's cosine theta, where I would have put the theta here, but it's the same as here. Cosine theta, I, and sine theta j. Can't get out of the way of the projector here. Your I component is the adjacent side of this. I keep wanting to do the theta back here. And your adjacent side is the cosine of that, and the opposite side is the sine. Okay, that is your unit vector. Well, yeah, it is a unit vector. Some u vectors are not unit vectors, just in this. Where theta is the angle of the vector that the vector makes with the positive x-axis. That's angle theta. Now, what they did, rather than drawing the theta there with the u, they projected u parallel to u, same direction of u, onto, moved it over here until it intersected the point P that we were looking for. And x sub 0 would be whatever that distance is out to the x-axis. Y sub 0 is that tiny little distance in the positive y. But, take this unit vector and make it parallel, make the vector go through the point P, and then extend it indefinitely to give you the line L. Okay? Now, that's the direction we want to know what the slope of the graph is. Okay? Now, it looks like this is the surface up here. So P on this surface would be somewhere maybe about there. And in that direction, what is the slope? What is the slope of that in that direction? That's what we're moving toward. Because down here, this is in the xy plane. Down here, the surface is up there. Okay. To find that desired slope, reduce the problem to 2 dimensions by intersecting the surface with a vertical plane passing through the point P parallel to u. That's why they drew that line the way they did. This is down here on the xy plane. And this is your x0 here, your y0 there, a tiny little amount there, and then your z is your f of x0, y0. Okay? So that goes up and intersects at this point C. And this projection of that unit vector onto the line, in the same direction as that unit vector, but going through this point P, okay? This is what projected onto the surface. There it is, okay? As I said, it looked like it was going downhill moderately right there. Okay? The slope of the surface at x0, y0, f of x0, y0, that's your z0, in the direction of u is defined as the slope of the curve C at that point. Curve C is the curve on the surface of that shape that is above x0, y0 and contains the point z0, which is f of x0, y0. Okay. Now, informally, you can write the slope of the curve C as a limit that looks much like those used in single variable calculus. The vertical plane used to form C intersects the xy plane in the line L, represented by the parametric equations. Okay. Let's go back here and see if we can find these. Remember, this is the angle theta here, and from P to some Q that also is on that line, okay? That line that you got from taking that unit vector here, parallel to that through the point P. On that line, T is how far out you went. If sort of hard to say. It's a parametric, it's a parameter that has you moving away from point P, okay, along that line, okay? So your X equation would be your X0, which is how far out you were to see X0, Y0 are that point, okay? And then you've moved out the line T times cosine X in the cosine theta in the X direction, and T times sine theta, that's in the Y direction, okay? So these parametric equations then refer to that. This gives you your starting point, and then this tells you how far out from that you've gone. So that for any value of T, the point Q of XY lies on the line L. Can't be otherwise. For each of the points P and Q, there is a corresponding point on the surface, X0, Y0, F of X0, Y0.
I'm trying to find L.
L, you go back, it's that first line that you had right here. That is the L. And then on the next slide, they still have the L there, they just don't name it. This point that goes through, the line that goes through PQ, because Q is on the L. So the previous slide said that's the line. Now you got a Q that's on that line. You might have written it down, but they didn't. Okay. All right. So for each of the points P and Q, this is point P, X0, Y0, and then up there, F of X0, Y0, and Q, which is X, Y, F of X, Y, that's up there, but it's on Q down here is on the XY plane, it's on the line L, and then when you project that up, using the function f of xy, that puts you up on the point above your point Q. Okay. Moreover, because the distance between P and Q is simply that, and this is almost shady looking, isn't it? Okay. If you go back a couple of slides, this one, rewrite this as x minus x0 is equal to t cosine theta, and that one's y minus y0 is t sine theta. Then, since you're doing the difference between x and x0 and y and y0, okay, and you're squaring that difference because that's how you get under the radical. So this is the distance between the 2 points, and this is that one, this is that one, the squared. Since they're squared, that would be the square root of t squared. Factor that out, that's just going to be an absolute value of t, and then cosine squared theta plus sine squared theta is 1. Okay? So you can, excuse me, write the slope of the secant line through x0, y0, f of x0, y0, and xy, f of xy. Okay? Let's go back and see what that secant line is they're talking about. That's the straight line that goes between these 2 points here. Okay? This is a curve. The straight line that does that, of course, is going to be a little bit shorter than the curve, but it's going to be pretty reasonable. Okay? Now, I'll take that back. We're on this line down here. X0, Y0, XY. That is the absolute value of T. Just that. This one, we have to also have under the radical the difference of those squares. That's not what we're dealing with here. So it's not up there, it's down here. Okay? Okay, the slope of the secant line through those 2 points. Yeah, you're.
T, is that T? Is that some small number? Is that equivalent to the delta X or delta Y?
It sure looks that way, and I think that's where it's heading, because I believe the next thing we'll be doing is letting T go to 0. So you're absolutely right. That is what that is. But what I was trying to see here, because when they talk about the slope of a secant line, you don't have a secant line between 2 points on a straight line. It's got to be this up here, okay? That has to be the secant line because that's your curve there. There's no curve down here, so I think it's got to be up there, what I said to begin with. But it seems like then the distance you'd have to have the z component in it as well. And they seem to be avoiding that like the plague, so. All right. So, the slope of that secant line will be alpha of xy minus alpha of, this is your z above q minus the z above p. That's what these are. Divided by t, because that's your parameter there. And this, going back, same place we did before, is x0 plus t cosine theta minus alpha of, comma, y0 minus y, or t sine theta.
Look, you got subscript 0, 0 in both components. See why you got x sub 0 plus t sub cosine theta. That's just the x sub 0.
Right, that's x. This thing right here is your x. So if you went back,
That's what I'm trying to look back to the original.
You see, there's the x.
Oh yeah, that's right.
There's your x and there's your y. How we first defined it. Okay, and the distance between p and q down on the xy plane is the absolute value of t. And then, so what they're doing next is as that distance is going to be getting closer, the difference between this and this as that gets closer. In other words, this is your z at q minus v of that. So that's going to be your distance up there. As that changes, as the t down here changes, this will then be, because those relations, this is f of x0 plus t cosine theta, comma y0 plus t sine theta, that's this one, minus alpha, that's just the same, alpha of x0, y0. Okay? They say that's the slope of the secant line. Change of z over the change of the distance that the xy is changing. Not x or y, but the total distance is changing. So this is, in gory detail, what that slope of that secant line is. Okay. Let's go back and see again. They didn't draw the secant line here, so it's the slope of this line that goes through here. Obviously going downhill because this is less, the x is less, the y is less. No, that y actually is a little bit more. So the x is, I can't say the x is less either. This x is greater, that y is greater, but the f for sure is less. So that's why. So your numerator is a negative, your denominator is positive. So you still get the slope is downhill. So yeah, that works out for whatever that's worth. Okay. Finally, by letting t approach 0, you arrive at the following definition. What this is your directional derivative, in the direction of that original u vector. Let f be a function of two variables, a function of two independent variables, x and y, and let u equal cosine theta I plus sine theta j be a unit vector, okay? And you know that has to be because this squared plus that squared is 1, okay? Be a unit vector, then the directional derivative of f in the direction of u is denoted by, okay, the capital D, whatever else you've had capital D stand for, like differential operator, okay, and those kinds of things, forget that here. This is directional derivative, capital D here, directional derivative in the direction of that unit vector u, that unit vector right there, of the function f, okay, is this limit. The limit is t approaches 0 of this thing minus that. All right, now notice something they've done here. Ooh, this looks tricky to me. Back here, that was x0, y0 here. The xy were, that would be f of xy. But here they're saying this is f of xy. So this is, oh, I see, okay. They just dropped their zeros everywhere, okay? Because remember, this was x of 0 and y is 0, that was x0 and y0. So now we're saying at any point xy, not a particular point, any point xy, then this will be your definition of your directional derivative, provided that limit exists, okay? There may be circumstances where it would. Calculating directional derivatives by this definition is similar to finding the derivative of a function of one variable by the limit process. A simple formula for finding directional derivatives involves the partial derivatives f sub x and f sub y. Okay. So let's see how that goes. Make sure I'm not skipping anything. Yeah. If f is a differentiable function of both f, x and y, independent variables x and y, then the directional derivative of f in the direction of some unit vector u cosine theta I plus sine theta j is, this is it, okay? The partial of f with respect to x times the cosine theta plus the partial of f with respect to y times the sine theta, okay? Now, a few things to note here. Your directional derivative is not a vector, okay? There's no I or J anywhere in either one of those, okay? The directional derivative is in the direction of a unit vector, but its value is not a vector quantity, it's a scalar quantity, okay? All right. Kind of hang on to that thought, sort of. I don't know if it's an important thought, but just that it is. And the same thing was true there. These are all scalar quantities. There's no vectors involved with them, so they haven't pulled a fast one here. So, there are infinitely many directional derivatives of a surface at any given point. One for every direction specified by u. Okay? They just show either 3 or 6 of them here, depending on if you align in one direction or the other. Okay? Here's your point, x0, y0. Okay? So they're dropping the zeros here. These are various directional or vectors. A vector in this direction, that direction, that direction. Looks like 6 different vectors there. The surface is up here. That's the blue curve here. And at the point of intersection, if you were to put a plane there that's tangent everywhere there, all these vectors here would be in that plane. Okay? And these would be the directional derivatives, one in each one of those directions. Here, 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 or here. Okay. Now, it's really tough for me to figure out where on this curve it is. It almost seems like this is tangent and parallel to the plane down here. It may not be. It doesn't necessarily have to be, but then the orientation.
Well, isn't the red figure there? Isn't that the plane?
The tangent plane at that point. Yeah.
Yeah.
At the point of
this is a surface of curve.
Yeah, that surface is turning. What I'm saying is this plane could be in any of these things. They've drawn it, making it look like it's at the maximum point. Or to me, it looks that way. It looks like this plane is parallel to that plane, which would mean at the peak. Doesn't have to be, okay? That's what I was saying. This plane could have been drawn anywhere on that curve, just depending on where you set that. That was the thing that bugged me. It was so symmetrical. Okay. 2 of those are the partial derivatives with respect to x and y. So let's see. This one looks pretty close to being the partial with respect to x. It may not be. It looks like it's angled a bit toward a negative y there, but it's pretty close. This one looks like it's pretty close to being the partial with respect to y. Okay? But you could twist them a little bit any direction and you have them going all over the place. But there's infinite number of them. Okay? 2 of them are that. The direction of the positive x-axis, theta equals 0, then your u would be, this would be I, just I, plus 0 j. Then the partial with respect to I would just be f of x, y, f sub x, partial of f with respect to x, y, because this one would be 0, partial of f with respect to x. Direction in the positive y-axis, that's where theta is equal to 2 pi half, then this would be 0, and this would just be 1j or j. Partial in that direction, either that u or this j, it doesn't matter, they're the same vectors, would be the partial. This is 0, this is partial of y with respect to x. Sine this, sine of pi half is 1, so that's what this is. Need more to see it to clean the board. Oh my. Oh. Now. Here's example 1. find the directional derivative of f of x, y equal 4 minus x squared minus 1/4 y squared. That's your surface, okay? At the point 1, 2. Okay. One thing that I think right off the bat is I want to figure out what the z is at 1, 2. Okay? So f of 1, 2. You don't have to do this now. It may not even be a good time, but I just want, that would be 4 minus, and 1 squared would be 1, minus 1/4 of 2 squared. Well, 2 squared, you know, y squared, which is here your 2 squared, would be 4, and 1/4 of that would be 1. So this would be 2. So your value in the z direction of your f at 1, 2 would be 2. So this point is at 1, 2, 2. 1 for x, 2 for y, and 2 also for z. Okay. Now, it's in the direction of cosine pi thirds I plus sine pi thirds j. Well, we sort of should know what sine of pi or cosine of pi thirds is. What is that? That's 1/2 I plus the sine of pi thirds. Square root of 3 over 2 times j. Okay? That's your unit vector. Oops, unit vector. Now, just to make sure I did it right, let's see. If you square this, you get 1/4. Square that, you get 3/4. 1/4 plus 3/4 is 1. So yeah, that is a unit vector. I like to check things, especially when they're sort of easy that way. Okay. So, we want the directional derivative of this function, not that we need that point there, but that function in the direction of this vector down here. Okay? So, what we just learned, the directional derivative in the function in the direction of this unit vector u of this function here, f of xy. I can't remember, did they put parentheses around that or not? No, they just did. Okay? That's equal to the partial of f with respect to x at xy. Let's go on and put in 1, 2. I don't see any reason of carrying around an xy when we don't need to. I guess maybe the first time we wrote it, we probably should put xy, partial xy, cosine pi thirds Goodness, my writing gets so sloppy if I start looking or thinking ahead, the writing just loses it. I don't know why that spot won't come out. Okay, it bugs me, but maybe it'll just disappear in a minute. Okay.
The second one, the side of that, is
Yeah.
okay, we still put in the 3 over 2 there.
Yeah, well, you could just put 1/2, yeah. Pi thirds plus partial of f with respect to y at xy times the sine pi thirds. Okay, let's just go back and make sure. Yeah, partial, yeah. where did they say back here that we're dealing with the point? Oh, it's F for theta equal, yeah, okay. All right, so I think that's correct. Except my Y disappeared here. I knew it was doing some strange things there. Okay. So, one thing we've got to do is find partial of F with respect to X. What would that be?
0 minus 2x.
Minus 2x. Partial of F with respect to Y is?
1/2 y. Minus.
Yeah, minus 1/2 y. See, if I'm paying attention to something else, my hand drifts just anywhere, okay? Minus 1/2 y. 10 o'clock scholar again, huh?
Yeah, I take my kid to the doctor.
Oh, sorry. Okay, we're in section 13.6, still in chapter 13, functions of several variables. 13.6 is directional derivatives and gradients. Right now we're on the directional derivatives part, and we're doing example 1, which is on page 921. Okay, so we're getting the partial of F with respect to X was minus 2X. Partial of F with respect to Y was minus. That minus is in a weird place, so let's get it down a little bit more reasonably. Minus, I think my screen was falling back on me at the point, minus 1/2 y. Okay? Now, okay? So that directional derivative in the direction of u, and I could write down what u is, but it's just such a pain in the neck. Let's just leave it as u, of f of 1, 2, that's the values for x and the value for y, and this would be the partial of f, which is a minus 2x evaluated where x is equal to 1, right, times the cosine of pi thirds, which we know to be 1/2, plus the partial of f with respect to y, we know, yeah, right there it is, minus 1/2 y. Y is 2, so that would be a minus 1. Okay. Okay. Oh, I wasn't plugging in yet. I knew there was something looked weird here. 1/2 y, and this is evaluated where y is equal to 2, because that's your value there. And this is times square root of 3 over 2. All right, this is just strung out all over the place. So this is a minus 2, right? Minus 2x, where x is 1, that would be a minus 2 times 1/2 minus a 1/2 times, no, minus a 1, because you're plugging in y equal 2 there, minus 1, which I'm just going to leave as a minus sign, I'm trying to square root of 3 over 2. All right. So this will be a minus 1 minus root 3 over 2. So that's going downhill, okay? And they have that to be minus 1.866, which seems reasonable to me. And the point is at 1, 2, 2, which we already said. And let's see if we can get a picture of that. Okay, so let's clear my writing. Goodness gracious, my back itches like crazy. Because f sub x of xy is minus 2x, just like we did, and f sub y at xy is minus y over 2, I said minus 1/2 y. Both of those are continuous functions. F is differentiable, and you can apply theorem 13.9, which says the directional derivative in the direction of this u vector here of the function f of xy, which is that one, that's the surface, okay, is the partial of f with respect to x times the cosine theta. That gives you sort of the direction in the positive x times plus f sub y, which is not on the screen anymore, but that would be your minus 1 times the root 3 over 2. All right. So, minus 2x cosine theta plus a negative y over 2 sine theta okay. Because f of x, both of these are continuous, f is differentiable, you can apply that. So this thing here becomes minus 2x, that's what partial of f with respect to x was, cosine theta plus partial of y with respect to, partial of f with respect to y was minus y over 2 sine theta. And evaluating at theta equal 1/3 for both of those, x equal 1 for that one, and y is equal 2 for that one, because our point was 1, 2, then this partial of the directional derivative in the direction of the unit vector u of f at 1, 2, x equal 1, y is equal 2, is minus 2 from here times 1/2 minus 1 from here times root 3 over 2. And that then left is simply negative 1 minus root 3 over 2, which is a pretty negative slope, or directional derivative. Here's a picture of that, and you see indeed that is the case, negative 1.88866. Here, yeah, you're 1, 2, 2. Okay, there's your point on this surface. Well, this surface has a max at 3. Now, by the way, this is a elliptical paraboloid. Okay, paraboloid because it's opening down. This is your z is to the first power, your x and y is to the second power. So that's a parabola on the xz plane like that. And this is a parabola on the yz plane like this. So that's a paraboloid. Max it at 4, because x equals 0, y equals 0. That's the maximum level ever reaches 4. And then you're twisting from this point here, 1, 2, a unit vector in the direction of 1/2 on the x and square root of 3 over 2 in the y. So a little bit stronger toward the y. But what you're going, that's the u vector. What this is going to be doing is, I think that's what this line is here. That's the slope going down here. Pretty strong negative slope, okay, because you're well onto the curve there. I guess this is, oh, okay. I was wondering, what is that arrow coming out of there for? that's part of the x-axis. Yeah, now I see. This part is under the curve. This part is out of the curve. All that is under the curve. Back here, this is up under that side. All that back here is under the curve. Okay. Doesn't seem too exciting yet, does it?
Maybe.
All right.
How does that relate to physics? Like, is that,
What's that?
does that relate to physics in any way? Like,
Yeah, it does. We're probably going to see a little bit later. This goes to Bill's question about something we did earlier. If your model here was describing how something is changing, say in the atmosphere with altitude, so your Z is going to be your altitude, and so you have pressures and stuff like this. So this could be your wind speed or something like that. So you might have something coming down like that. Pretty strong gradient downhill there. Okay, but before we get to this, there is example 2. So let's go back up and use this space to do example 2. Now, example 2 is also located at larsoncalculus.com, and there you can see an interactive version of this type of an example. So it says, find the directional derivative of f of xy, and this is equal to x squared sine of 2y. Okay. At the point 1 comma pi halves goodness gracious. Just gets worse and worse. I was just trying to kind of picture where this would be. In the direction of, here's our unit vector. Happen to call this one V. And guess what? It's not a unit vector. Okay? I did forget to read that sentence above here. Okay, should have done this. I saw it earlier and thought we got to say this, and I forgot to. You have been specifying direction by a unit vector u when the direction is not given, or is given by a vector whose length is not 1. You must normalize the vector before applying the formula that we just had. You've got to have a normal unit vector there. So now we want it in the direction of v, and v is 3i minus 4j? Yeah. So what's the first thing we got to do? Okay, we're going to have to do that at some point. And if you want to do it now, there's no hurt with doing that. So f sub x of xy is going to be what? It's what? 2x sine 2y, right? That's the other part of it. And f sub y is? Okay, yuck. Goodness gracious, this thing. The pen just keeps leaving little marks all over the place. And I'll say, what is that there for? Okay. Okay. All right. Yeah, okay. Now I got you. 2x squared. The 2 from here, the x squared from there. I was thinking you were differentiating the x squared again. I said, no, that's not. Okay. 2x squared cosine 2y. Perfect. Okay. All at once. We did the, okay, the 2x's came down. I'm sorry, the x squared came down. The derivative of sine is cosine of 2y. and then you did the chain rule for that, and that gave you the 2 alpha. So yeah, perfect. Now, okay, those needed to be done. We're not ready to use them yet. What do we have to do before we get too far along here? Say again?
Magnitude of V.
Yeah. What is the magnitude of V?
5 V squared plus 4 squared, 25 square root 25 is 5.
5. Okay, and what do you do with it?
You set the I over 5.
Yes. So now the unit vector in the direction, I'm going to put IDO of V, in the direction of V, that's my shorthand, is 3/5 I minus 4/5 J. Now I always like to go back and check real quickly that this is a piece of cake to do. Make sure that's the unit vector. This is where it is. 9/25.
Oh.
This is 16/25. Add them together, you get 25/25. So yeah, that is a unit vector. Okay. Now, that is what's equivalent to our cosine theta and sine theta. Okay. We don't need to know what the theta is. That wasn't necessary. It's just what those values are. Okay. Now I think we're kind of ready to go, aren't we? We're looking for a directional derivative that in that direction. So this is directional derivative in direction of this new unit vector u at, oh, didn't do anything with that yet, did we? Okay. There's my function. I was losing my function here. 1 squared is 1, and sine of pi is what? 0. So this point is going to be 1 pi halves 0. The z is going to be 0. The f of xy is 0 there. Okay. Now, f of 1 pi halves is equal to what? Write it out in general form first, just to get used to it. F sub x times, which is our 3/5. Oh yeah, let's just go and call it cosine theta because I'm doing the other generically, so let's do that generically too. Cosine theta plus f sub y sine theta. Okay, so now we can plug and chug here. F sub x is there. Now let's do, you don't have to do it this way, f sub x at 1 pi halves would be okay. The sine of 2 times pi halves would be pi, right? The sine of pi is 0. Okay, how about f sub y at 1 pi halves? Okay, and you're right there. That would be, well, not quite, but close. 2 times 1 times, okay, say again? Negative 2. Perfect. Perfect. Okay, so now that we've got those in, it's easier to write. The first one is just 0. So now we have a minus 2 times a minus 4/5, which is 8/5. Goodness, we went back and forth, plus, minus, but found up being 8/5. Okay? So this value here was minus 2. This value here is minus 4/5. And no matter what this value was, that's a 0, and yeah, this was the 3/5, but it didn't matter anyway. Plus of x was 0. Okay. Now, this happens to be your awfully close to being your f sub y, because your x component is partial with respect to it. So anyway, it comes out 8/5. So that was example 2. Why didn't I think of drawing this graph? Okay, I'm not even going to consider it. Okay, I don't know how long I can hold it. Do it. This is what that graph looks like. This thing right here. Oh my word. Okay. When sine, which ends in the x direction, is positive, this thing's going up. Oh boy, what a mess. I don't know why I didn't want to draw this, okay? The unit vector is there. Positive 3/5 minus 4/5. Positive this direction, minus in that direction. That looks about right. Okay, there's a point 1 root 2, and what was the other? 0. So we're right there on the xy plane because your z component is 0 there. And what is your directional derivative there? Looks like it's heading uphill pretty fast, and it is 8/5. That's pretty good. I can't even follow this curve here. I can't tell where it's up, down, or whatever. It's just, but it does look like you're okay. They could just draw anything there, and I'll take your word for it because I don't see those things well at all. All right, so let's move on to the gradient of a function of two variables. The gradient of a function of two variables is a vector-valued function of two variables. Directional derivative is a scalar quantity, okay? It just tells you where it's headed, okay? Sort of like a slope, on a single variable equation, okay? A gradient, though, is a vector-valued function. So here's the definition of a gradient of a function of two variables. Let z is equal to f of xy be a function of x and y, independent variables x and y, z is the dependent variable, such that f sub x and f sub y both exist. The partial of f with respect to x, partial of f with respect to y both exist. That means you can't have any vertical planes or anything in those directions. Okay. Then the gradient of f, denoted by, and the only name I have for this is they call it del f, and sometimes they call it grad f. I kind of prefer grad f, but it kind of looks like a delta, but it's upside down. So that's why I usually don't say del, because I think I'm saying delta, but it's not. It's del f. Okay. Okay. That's what it represents gradient. Notice they bold it. I can't write that bold, so when I write that, I put an arrow over it, indicating that is a vector. And that is the partial of f with respect to x in the I direction, partial of f with respect to y in the j direction. That's your vector function. Okay? Another notation for the gradient is given by grad of f of xy. Okay? Now, I see it on calculators all the time. They'll say degrees, radians, and grad. And I think, how in the world can they express this? Because that's a vector in that. So I haven't ever even investigated to see what they mean by that grad. Seems like there'll only be one grad, but I don't know how they do it there, so don't ask me, okay? But in this figure down here, 1348, note that for each xy, the gradient del f of xy is a vector in the plane, not a vector in space. okay? It's only in the XY direction, okay? So it's not something up here, it's down here, okay? It's a vector in the XY plane. Now, if this is your Z up here, we don't have any idea what the function is, but it's some function here. And this is your partial of f with respect to x, which obviously, or looks at least to me like it's going downhill here in the x direction, and going downhill here in the y direction. That gives your grad, or your del, heading towards 0 here too. Okay? But in that direction, you have your maximum, well, I'm jumping ahead here, it's your maximum slope in the direction of that grad. Okay? Because this is a partial of f is negative, partial of y is negative, so this I is negative, that J is negative. You're heading in that direction, and yet that has you pointing to your direction of maximum slope. Now, we haven't gotten there yet. I'm just telling you that's going to be the case.
Like, it looks like it's going to the maximum slope.
It surely does. Yeah. Huh?
Like up?
Yeah.
Okay.
Yeah. In the Z direction there. We haven't gotten that far in the book yet, but I'm telling you that's going to be the case. Even though both of those are negative, your gradient is pointing in the direction that's going to take you maximum, which is kind of strange, but true. So here's example 3. It says, notice that no value is assigned to the symbol grad itself, or del itself. It is an operator in the same sense that d by dx is an operator. I like saying d by dx. Okay. When del operates on f of xy, it produces a vector, which is del f of xy. Okay. So here's example 3. How are we doing on time? Whoa! Goodness, this has slipped by, hasn't it? Find the gradient of f of xy is equal y log x plus xy squared at the point 1, 2. All right. A couple things first. This is a scalar function. No vector qualities of this at all. It's just a scalar function. It's describing some x and y down here, some surface up here, doing something. Doing something weird, but doing something. Okay. So I always like to figure out what the next coordinate is. So if it's at that point, what is your function there? F at 1, 2 would be what? At 0. Four, exactly. Okay, so up there on the graph, this point is 1, 2, 4. Now it has nothing to do with the problem right now at all, but just I kind of like to make sure. Part of the reason I like to do that is if that would have been at 0, 2, as soon as you look at this, you say, nope, you can't do that because you can't take the log of 0.
Before C would be 4.
The Z is 4, yeah. So I put the order triplet up there.
Okay, I didn't know that.
Exactly. All right, so find the gradient. What are a couple things you got to find? In fact, the major things you got to find. F with respect to x, and what would that be?
1 y over x.
Y over x, good. Y squared, perfect. Okay. Now we want that at 1, 2. So what would that be? 6 is what you said? Yeah, okay. I thought you made a grunt or something. Okay. All right. What's your F sub y? We'll start with xy. So I'm going to leave that off for now, just like we did before. F sub y would be natural log of x
plus
2xy. Perfect. And what is that at 1, 2?
4.
Yep, 4. All right, pretty interesting, huh? So what's the gradient of that function at the point 1, 2? Del f at 1, 2 will be
4i.
no 6i,
Oh,
isn't it?
6i.
6i
Plus 4j.
plus 4j. That's it. That's it.
Seems
All there is to it.
too easy.
I know. I'm sorry. I wish I could make it harder, but I haven't figured out a way to do that yet. They managed to do that. It looked like to me they kept the x's and y's in there a long time before they finally put the values in.
Yeah.
I got rid of them a little bit sooner. Okay? Because the gradient of f is a vector, you can write the directional derivative of f in the direction of u. Oh, yeah, okay. Interesting. The directional derivative of, in direction of u, of the function f of xy, this is any old f of xy, not just the one above, that's equal to, if you remember the formula, it's right, where u was cosine theta I plus sine theta j, right? Okay, and since your gradient of f is equal to partial of f with respect to x I plus partial with respect to y j, then the dot product of these two is this times that, which is that, plus this times that, which is that. And remember, dot products yield a scalar, and this is a scalar. So guess what? We just found another way of getting it. You're doing the same thing, but if you know this not as cosine theta I, as 17i, no, it has to be a unit vector. Whatever the values are there, yeah, you just dot those together. So what they're saying here is the directional derivative in the direction of u of the function f of xy is the gradient, and that's a vector, so I always put, I don't always do it, do I? Okay. How many times did I miss it? The gradient of f of xy dotted with u. Okay? That's it. So, almost this notation here, since that's subscript to put it, it doesn't matter where you put it. You can put the u first. Okay? Dotted with that. This dotted with that. Dot products are commutative. Okay. Now, do we have time for example 4? Oh, wait, we haven't done example 3 yet. I forgot that, sorry. Haven't shown you how they do example 3. F of x is just like you said, y over x plus y squared. F sub y is, goodness, the glare is terrible, log x plus 2xy. The gradient of f then would be f sub x I plus f sub yj, and they put it all in there. They didn't go and calculate it at that point, but we can live with that, okay? And then at the point 1, 2. Now you put it in, and that would be 2 over 1, which is 2 plus 4 is 6i, and this is 0 plus 4j. 6i plus 4j. All right, and then, I'm sorry, here's what we just said. The directional derivative and direction of view of the function f of x, y is the partial of f with respect to x in the I direction plus the partial of f with respect to y in the j direction. That's your gradient, dotted with cosine theta I plus sine theta j. That's your u. In other words, the directional derivative is the dot product of the gradient and the directional derivative, and the direction derivative, not the directional derivative, the direction derivative. In other words, what direction is going? U. Now, do we have time for example 4? What do you think? What time?
3 minutes.
3 minutes?
Yeah.
Probably not. Okay, probably not. So let's stop there, and we'll pick up with example 4 next time. If I can find my pencil here. Okay. Get my marker in place. And let's see how many homework exercises. Ooh, this is a long section. You can do either 3 or 5. They're both a Calc Chat. 3 is a Calc View. You can do either 7 or 9. They're both a Calc Chat. 7 is a Calc View. You can do either 11 or 13. They're both a Calc Chat. And I think you can do either 15 or 17. They're both a Calc Chat. Oh, I'm sorry, 15 through 19. They're all at Calc Chat. 17 is a Calc View. And using what we just found, you can try 21 or 23, or you can wait and we'll do that next time. Okay. Good deal. Any questions? Okay, that probably didn't take those 2 minutes up, but it probably came close.